Hello, in this video I'll be showing you how to answer the NSAA 2017 Section 2 question C2. At the start of the question you're given the following information. The lattice enthalpy in kilojoules per mole is given by equation 1. So lattice enthalpy equals minus 1.07 times 10 to the 5 times n ions times Z plus times Z minus all over R plus plus R minus, where n ion is the number of ions in formula unit. Z plus and Z minus are the absolute values for the charge of the cation and anion respectively. R plus and R minus are the radius of the cation and anion respectively in picometers, where 1 picometer is 10 to the minus 12 meters. Question A. Use equation 1 to calculate lattice enthalpy for CuF2, given that R plus equals 73 picometers and R minus equals 133 picometers. So CuF2 consists of a Cu2 plus and 2F minus, where here the number of ions equals 3, 1 plus 2. Z plus is the charge of the copper, that's 2, and Z minus is the charge of F minus, and that's 1, not minus 1, as here it states the absolute value for the charge. Now all we have to do is just sub in these numbers into equation 1. So you get the lattice enthalpy is minus 1.07 times 10 to the 5 times 3 times 2 times 1 over 73 plus 133, which you're given in the question. And that equals minus 3,120 kilojoules per mole. Part B. Use equation 1 to calculate lattice enthalpy for CuF3, given that R plus equals 54 picometers and R minus equals 133 picometers. This is essentially a similar question to Part A, except with different values. So for CuF3, we have a Cu3 plus cation and 3F minus anions. Therefore, the number of ions in the formula unit is 4. Z plus, the charge on the copper, is 3. Z minus, the charge on the fluorine, is 1. Subbing into the equation, you get lattice enthalpy equals minus 1.07 times 10 to the 5 times 4 times 3 times 1, all over 54 plus 133. And that gives you minus 6,870 kilojoules per mole. Part C. Determine the oxidation state of copper in each of the species in the following reaction, and hence classify what kind of reaction this is. So we have CuF2 plus a half F2 goes to CuF3. Firstly, we should note that F in ionic solids always has a minus 1 oxidation state. So to find the oxidation state of the copper, we know in CuF2 it's the Cu2 plus, and in CuF3 it's the Cu3 plus. So we have a 2 plus going to a 3 plus, and this is an oxidation, as electrons are lost. Next, we should note that the oxidation state of F in elemental F2 is 0. So going from a half F2 to CuF3, you have 0 going to minus 1, which is a reduction, as the F gains electrons. So since you have an oxidation and a reduction, this gives you a redox reaction. Question D. The enthalpy change for the reaction in equation 2 can be calculated using this Hess cycle. Use the results from Part A and Part B, summarized here, and the following enthalpy changes below, to calculate the enthalpy change for equation 2, which is CuF2 plus a half F2 goes to CuF3. If you want to have a go at this, please pause the video now. Let's start by looking at the cycle step by step and see what's happening. So here you have CuF2 plus half F2, and that goes to CuF3, where this is the value you're asked to calculate. So going up the cycle, you have Cu2 plus 2F minus plus a half F2. And this is simply breaking the CuF2 lattice from the solid to the gas. And this is a positive value, as the lattice enthalpy is given as going from the gas to the solid. So from going to solid to the gas, you flip the sign. Going up the cycle again, you have Cu3 plus 2F minus plus a half F2 plus E minus. And this is ionizing the Cu2 plus to a Cu3 plus. And this is given here with an enthalpy change of 3,555. Going down the cycle, you get Cu3 plus 3F minus. And this is the electron affinity for half a mole of F2. Here you're given the electron affinity for 1 mole of F2, but since we have a half F2, we take a half of 540. This is a common mistake students forget. They don't see that it's a half and just write minus 540. Going down the cycle again, you have Cu3 plus 3F minus going to CuF3. And this is forming the CuF3 lattice, which is the result we calculated in part B, and that's minus 6,870. So to calculate the value of x, we simply just go around the cycle adding the values. So we have x equals 3,120 plus 3,555 minus a half times 540 minus 6,870. And that gives you a total of minus 465 kilojoules per mole. Part E. Use the data below to calculate the enthalpy change of the following reaction. 2mF2 goes to mF3 plus mF, where m is an unspecified metallic element. You may find it helpful to start by using an appropriate Hess cycle. When it says you may, it essentially means you will. So to attempt this question, you must draw a Hess cycle. Looking at the data given, here is breaking up the MF2 lattice. This is breaking up the MF3 lattice. This is breaking up the MF lattice. This is the ionization of M plus to M2 plus. And this is the ionization of M2 plus to M3 plus. If you want to have a go at this question, please pause the video now. To start constructing the Hess cycle, we must first put down what we need to find out and then work our way from there. Next, we'll work up from our starting material. So in order to do anything, we must first break up this lattice. So we have 2mF2 goes to 2m2 plus 4f minus. You can see in the product that one of the m's is a 3 plus and one of the m's is a 1 plus oxidation state. So next, we will change one of the M2 plus, ionize it to an M3 plus. Yeah. So here we have one of M2 plus being ionized to a 3 plus. Next, we change the M2 plus into an M plus, and this is the electron affinity of M2 plus, or opposite of ionization. So now we have the M2 plus going to an M plus. So now we have M3 plus M plus 4F minus. Now the final step is to go to the MF3 and MF. And this is simply just forming the two lattices from their gaseous ions. So now we've constructed the Hess cycle. Now we just have to add these values into the right place. So breaking up the MF2 lattice, we have a value of 3,000. But note, we're breaking up two MF2s, so you do 2 times 3,000. Next, the ionization of M2 plus to M3 plus, and that also has a value of 3,000. The electron affinity of M2 plus going to M plus, it's minus 2,000, it's the opposite of the ionization. And finally, forming the MF3 and MF lattice have the values of minus 7,000 as is the opposite of this reaction, and minus 1,000 as it is the opposite of this reaction. So to find the delta H, we simply go around the cycle. So delta H, 2 times 3,000 plus 3,000 minus 2,000 minus 7,000 minus 1,000. And this gives you delta H equals minus 1,000 kilojoules per mole.